Okay. Good morning to all. Welcome to everyone. As we come together to celebrate the life of an outstanding scientist, a great metallurgist, an efficient manager, educator, and policymaker in the realm of science, technology, and innovation, Padma Shri Professor Dr. Srikumar Banerjee, former Chairman, Atomic Energy Commission of India and Secretary, Department of Atomic Energy, and Homi Bhabha Chair Professor. In the words of our beloved Chairman, a down-to-earth person, a scientist with an ear for music. So may I now request Honorable Vice Chancellor, Professor P.R. Vasudeva Rao, for presenting his welcome and introductory remarks. Professor Vasudeva Rao, please.
Nurag, I can close the laptop. Respected Professor Kakotkar, Chancellor, Homi Bhabha National Institute, Professor Nirendra Manna, Vice Chancellor, BIT Mesra, and Chief Guest of today's function, Shri K.N. Vyas, Chairman, Council of Management, HBNI, and Secretary, DAE, Professor Joshi, Professor Grover, senior colleagues from various constituent institutions off-campus center of HBNI who have joined the program online, Dr. N. Sai Baba, former Chief Executive, NFC, faculty members, students, and other participants. We have gathered today here to pay our respect to our former Chancellor, Professor Srikumar Banerjee, who passed away last year suddenly on 23rd May. Professor Banerjee was an outstanding researcher, mentor par excellence, and a great human being, and also an excellent speaker. A very rare combination of the important intellectual qualities. Over the year, we have continued to feel his absence amongst us. A person like Dr. Banerjee, with immense contributions in science, technology, and education, is always a great source of inspiration, especially for the young minds. And it is for this reason that we decided to organize a program in his honor today. We also felt that we will use this occasion to ponder upon not only the greatness of Dr. Banerjee, but also deliberate on a subject close to his heart, material science, with a view to enthuse our young researchers to take up challenging programs of research in this domain. We are very grateful to Professor Nirendra Manna for immediately agreeing to our request and traveling to Mumbai in spite of his busy schedule. Professor Manna has made excellent contributions in materials engineering research for several decades. He has contributed to the higher education system in the country by steering IIT Kanpur, and he now serves as a great integrator of the engineering community in the country through his leadership of the Indian National Academy of Science Engineering, besides steering BIT Mesra. A very significant point is that he had been associated with Dr. Banerjee, and he has been associated with the HBNI also as a member of the academic council, and therefore he has keen involvement in the academic affairs of HBNI. We felt therefore that it's very apt that he delivers the first memorial lecture in honor of Professor Banerjee. We keenly look forward to his lecture. We are also fortunate to have with us our Chancellor, Dr. Anil Kakotkar, Shri K.N. Vyas, Chairman of our Council of Management and Secretary DAE, Professor J.B. Joshi, Professor Grover, and many others offline and online. We are also fortunate that Dr. N. Sai Baba, who steered the nuclear fuel complex as its chief executive, has joined us online. Dr. Banerjee was closely associated with his PhD program as the chairman of his doctoral committee. I cordially welcome all these dignitaries and convey our sincere thanks to them for sparing their time for this program in spite of the busy schedule. In his letter written to one of his friends, Dr. Homi Bhabha mentioned, and I quote, "The span of one's life is limited. What comes after death, no one knows. nor do I care. And this sentence is very important. Since, therefore, I cannot increase the content of life by increasing its duration, I will increase it by increasing its intensity. I think this statement was quite true also for Dr. Banerjee, who was engaged in every activity with intensity until the very last moment of his life. HBN is indeed fortunate that it had Dr. Banerjee as its chancellor. Now, coming to the subject of today's meeting, which will be deliberated by Dr. Manna, material science and engineering was an area in which Dr. Banerjee also excelled, and it will continue to be an important domain for DI. Whether it's clad materials for enhanced burnup, structural materials for enhanced lifetime, advanced materials for high temperature reactors and molten salt reactors, or host matrices for waste immobilization, we will continue to face exciting and important research challenges in these domains as we develop nuclear technologies. It is therefore very appropriate that we listen to perspectives from material specialists in this memorial program, and I am happy that we will have a renowned specialist in material science and engineering, Professor Manna, to deliver a special lecture today. And I am sure that his lecture will also be of high value to our students and faculty, considering the interest of DA with regard to materials development for its programs. And with these few remarks, I once again welcome all of you to this memorial program. Thank you.
Thank you, Professor Rao. Now we are going to have a display of messages in the memory of Professor Banerjee prepared by Ms. Aishwarya.
education has been an integral part of the department's activity right from the beginning. The training school program of the department started 64 years back and is still running very strong. And this is the world's longest nuclear science and engineering education program. It can also claim that the entire technology development indigenously done in the country has come out from the work of those who have been graduated from this training school of the Bhabha Atomic Research Center. So HBNI is a natural extension of this program. Those who have been working in the department for an extended period, sometimes even their entire career, they are having that experience of seeing that their own work, their own research is getting translated into the technology development in a very massive way. This is a very great feeling at the end of the career of many of the scientists who have gone through this within the department. Now that experience can as well be, at least the taste of that experience can as well be given to the students who are coming from outside to the department for their doctoral work. And that is one thing which HBNI can claim to give and which I believe no other institutions in the country, no other universities in the country can provide.
Thank you. May I now request Professor Anil Kakotkar, Chancellor HBNI, for his remarks. Professor Anil Kakotkar, please.
This is the mic, it should not matter.
Oh, thank you.
Dear colleagues, both present here in this conference room, as well as all those who have joined us remotely. I want to begin by thanking Professor Vasudeva Rao and the HBNI team for organizing this event, Dr. Srikumar Banerjee Memorial Program, and also organizing a lecture, memorial lecture in his honor. And we are very fortunate that we have Professor Indranil Manna deliver the first such Dr. Srikumar Banerjee Memorial Lecture. As we just heard Professor Banerjee himself about the role HBNI has been playing as a natural extension to the long-standing training school activity and the important role of connect between basic research as well as its real life applications. I think is a theme which is close to everybody's heart in the Department of Atomic Energy, at least. And I'm sure that message is increasingly getting traction throughout the country with the so-called emphasis on Atmanirbhar Bharat, which to me is a restatement of what Dr. Bhabha used to say about self-reliance. I remember several interactions I have had with Dr. Banerjee, very close in many aspects. But I was just debating to myself, how should I describe him today? And I would describe him as a very, very cultured scientist. We, to talk about it in the our own Indian languages, Hindi or Marathi or whatever. So there was something about a great Susamskrit individual about Dr. Banerjee. And that describes, I think, his multifarious interests, both in science and outside science. And I think that's an essential attribute to be a complete person, complete individual. And Banerjee certainly was an excellent case, excellent individual, an excellent example for everybody to emulate. Talking about material science, or material science and engineering, which is the theme of today's program, I have, because I being on the engineering side and Dr. Banerjee being his physical metallurgy related work, material science related work, mostly essentially focused on zirconium and the alloys. So I, being at the user end of those alloys, I had several interactions with Dr. Banerjee. And it's not that we agreed on, there are also disagreements. But I think that spirit of inquiry in everything that needs to be looked into in a holistic sense is something that was a great bond between both of us. And I just remember one particular event or one particular discussion where we develop materials in the lab, and most of the material labs, we're talking specifically in the context of facilities and metallurgy division of Bark in those days. So they would have small facilities to create small nuggets to create samples for carrying out evaluation and research. And then the question was whether that data is applicable when you go to NFC, at least for atomic energy related material, where you would produce the same material in a much larger scale. And obviously there were surprises. Relating that data has been a challenge at times, because there is always, and this is scale effect is a very common thing. It's common in all, it's common in fluid mechanics, it's common in structural mechanics, it's common in materials, everywhere this is. So while discussing about this problem, Dr. Banerjee made a very pertinent point at that time, which I still remember. And that he said that, look, we do work in Bark in gram scale. Of course, there are a few facilities where we do in kilogram scale, but mostly new material in gram scale. And when we go to a production factory, whether it is NFC for zirconium alloys, or at IGCAR, a lot of work has been done with SAIL for the steels required for pulp. But there we are talking about ton scale or tens of ton scales, and in case of steel, even larger. Now, translating the knowledge, translating the data, translating information, he felt that we need an intermediate scale facilities where one can do work and then you bridge this gap. So he was talking about ability to do work in maybe hundreds of kilogram scale or ton scale, which we did point out that that's a gap in our infrastructure. Today, of course, I'm not saying that that gap is bridged in everything. A few areas this gap is bridged and people are approaching other institutions, but still it becomes a very circuitous route. Because getting this done in different organization is an important thing because that is how we leverage our resources. But when there is urgency, this becomes a problem. And so I think it's still worthwhile looking at these gaps so that we have complete. So I don't want to prolong this. There are many aspects which probably are even more important than this, and I'm myself aware of, again, the discussions with Dr. Banerjee. But all I want to stress is this understanding that whatever we know, of course, is important, but whatever we don't know, awareness of that also is equally important. And that is something missing, and that is what we can clearly learn from Dr. Banerjee's life and his being with us for so long, and for us to be able to carry the program forward. So let me use this occasion to pay my respects to the memory of Dr. Banerjee. And I think it's only important that we capture the key points of the legacy and build on that. So that is how the institutions grow. That is how the individuals in the institution grow. And so I compliment you, Professor Vasudev Rao, for initiating this. Thank you.
Thank you, Professor Kakotkar, for sharing your scientific memories of Banerjee. So may I now request Sri K.N. Vyas, Chairman, Council of Management, HBNI, and Secretary DAE for paying his remarks. Please.
Thank you very much. Respected dignitaries present here, respected Kakotkar sir, Chancellor HBNI, Professor Manna, today's chief guest, Professor Vasudev Rao, Vice Chancellor HBNI, Professor Grover, Professor Joshi, other colleagues present online and in this hall as well. I would like to narrate two incidents which I had with Banerjee sir. That was the first time when I was really having close interaction with Banerjee sir. It was, if I guess it correctly, it was Viva Vose, midterm Viva Vose of training school, 33rd or 34th batch of training school. He was the chair of the committee and I was one of the members. I used to teach those days reactor engineering, few lectures. And I remember generally his disposition was relatively okay. He used to be lenient in giving marks also. But one of the students in metallurgy, he had made some major, I could not understand really how big was the mistake, but there were some mistake in his fundamentals. And in that case, I found he was very strict. In fact, another material science specialist was there, that how come we have made this type of mistakes, the person, we have not examined his capability in this particular subject more thoroughly. So he was, even though otherwise the performance of the candidate was, the TSO was good, but he did deduct few marks for not knowing the fundamentals so very nicely. So academically he was very sound, and the way he conducted that particular part, giving hints, and then still making up his mind that the person does not have good enough fundamentals. So this is one thing in the subject which he knew very well. I found how he was examining the person. And second thing, in the field, which was not his key field, he was at that time director of BRC, and at that time few divisions of BRC had made can motor pump. Earlier can motor pumps were made by BRC for low pressure, low temperature system. In this case, it was for some of the RPG application, high temperature, high pressure can motor pump. Some work was done by reactor projects group, specifically Mehra sir and Udge sir. They had worked out the design detailing and then tolerances and so on. Rest of the work done by in the design by RCNT, that E&IG, Shiban Bhattacharya sir was there, who had designed the can motor, and remaining work by Central Workshop, I think Sutar sir was there and Mr. Javle was there, and some work on silicon carbide by Materials Group, and some feed throughs glass metal seals, something like that. Now, the particular program was in Central Workshop, no, sorry, not in Central Workshop, in Goal Canteen, where the acoustics was not good. And he listened to everyone. We were not able to hear many of the things which were being spoken by various developers. But when his turn came, acoustic became automatically very nice. Somehow, I do not know, he had that sound quality. And he could pick up these key points from each of the development, and he could so lucidly connect everything. And then, because I think Professor Vasudhara also said about his ability to speak very nicely. He could connect everything so very nicely, and so that even in the field which is not his, I would say, key field of interest or key field of expertise, but he could connect everything. So I think very unique quality, that academically it is not only you are sound, but you have very good grasp of the fields which are not directly connected with your area of expertise. And I'm really thankful to Professor Manna today that in the field in which he was really the expert, Professor Manna will be giving us the key inputs. And I thank once again Vice Chancellor HBNI for organizing this particular function, and Chancellor HBNI for inviting me for this function as well. Thank you very much. Thank you. Thank you.
Thank you, Chairman, for sharing your nice memories with Professor Banerjee. Now we'll hear one of the reminiscences from Dr. N. Sai Baba, former Chief Executive of Nuclear Fuel Complex, a close associate and student of Dr. Banerjee. Now over to Dr. Sai Baba through online mode, please.
Thank you very much, Mr. Naik. Most respected Kakotkar Saab and most respected Indranil Manna Saab, my friend Dr. Vyas, Chairman, Dr. P.R. Vasudeva Rao, who has invited me for this occasion, and I'm grateful to him for that, Professor Naik, Professor Joshi, and all the participants who are watching directly and indirectly. A very good morning to all of you. A great scientist par excellence is Dr. Banerjee. He was a regular visitor to Nuclear Fuel Complex, and every time we used to look forward to his visit to NFC because it was always educating. He would always come, spend few days with us, 1 or 2 days, and then collect few samples and do all the studies at Mumbai. And then when he comes back in the next visit, he would explain to us what all he has done on those samples and how we should move forward to develop that particular material. In fact, his signature is inscribed on every zircaloy product that has come out of, that is coming out of Nuclear Fuel Complex. He's a master of this zircaloy science, And I want to touch upon two important products of a pressurized heavy water reactor. The first one is pressure tube or coolant tube, and the second one is a seamless calendar tube. And these two important core components are very close to his heart, and he has made very valuable contributions in this development of these two particular products. And I think these two products are the best in the world today, what NFC is producing for the PHWRs. To talk about the first product, that is the pressure tubes, it was very easy to produce zirconium alloy 2 tubes, and then came in information that zircaloy 2 doesn't have much life, and so we have to shift to zircon 2.5% niobium. So it was a huge task to shift from zircaloy 2 to zirc niobium. And I can remember 4 major stages in which Dr. Banerjee has made his contributions by making corrections in the material composition, in the temperatures at the intermediate stage and at the final stage, and also in the entire, as a process step. And after producing these zirc niobium tubes, he was very, very happy, and I can see his pride that at least we could produce in a short time, and we could replace the future reactors with zirc 2.5% niobium. But then immediately came that the hydrogen cannot be 25%, it has to be less. In fact, every ppm of hydrogen will knock away 1 year of its life. So the task was to make a pressure tube of 5 ppm and not more than 5, so that we can get 20 years of the life of this pressure tube component. And this, he has very ably assisted us, and with his assistance, we could come out, and every tube produced in nuclear fuel complex did not cross 4 ppm. And then the final phase, where he has made greatest contributions in adjusting the mechanical properties from one end to the other end, uniformity, and also the microstructure that gives excellent creep resistance, and so that the longevity is the highest. And in this endeavor to meet this particular task, he has made several suggestions, and in fact my PhD has been part of this technology understanding. And I am very grateful to Dr. Banerjee, because he made me understand. I am basically a mechanical engineer, but then I have learned metallurgy mostly under him and in his department. Then the second part is the seamless calendar tube. But for him, I think the seamless calendar tube wouldn't have been a reality, because there were many doubts that if it fails, the failure can be catastrophic. But then he did prove that after making 2 years of irradiation to influence of neutrons, and then finally he proved that this seamless calendar tube can withstand as good as the welded tube, and he is the key author who has supported our cause. And then today we have in every reactor a seamless calendar tube only, and not a welded tube. A Canadian specialist who visited nuclear fuel complex, he tried to see that 5-6 seamless calendar tubes, and then he was trying to see from both ends to locate a weld. So he was not able to believe. Then we told him that we have made hundreds of seamless calendar tubes, and we have also been successful in testing a seamless calendar tube to failure to a high pressure. The special personal traits of Dr. Banerjee are many. Basically, he is a teacher, and he can explain any topic in which the listener is not a professional in that field, and that also he will make him understand very nicely. And I am an admirer of his speeches, or his presentations, and wherever possible, I don't miss his presentation. On one such occasion, when I visited Bombay to BRC, I came to know that Dr. Banerjee is giving a talk on all the activities of Bhabha Atomic Research Center, almost for 2 hours period. It was music to the ears because till the time I never knew that so many jobs are being done by BRC. The way he has covered each and every job, it's mind-boggling, and it's only he can present such a wonderful presentation. And Dr. Banerjee, his biggest contribution is structure-property relation in zircaloy materials. So what structure is required to meet the end product properties? That is the biggest contribution by Dr. Banerjee, and he is a master in the technology of zirconium alloy, and he is a great visionary. And today, almost all the products of nuclear fuel complex bear his signature, and they are the best in the field in the entire world. I can also talk about every product that he has made for the reactor programs, whether it's the research reactors or the operating reactors. And I thank Dr. Vasudeva Rao for giving me this opportunity to speak on this occasion. Thank you.
Good morning. I welcome you all on behalf of Homi Bhabha National Institute for our beloved Dr. Srikumar Banerjee Memorial Lecture. I welcome Professor Indranil Manna, chief guest of today's functions, and thank him for accepting our invitations to deliver Dr. Srikumar Banerjee Memorial Lecture. I extend a very warm welcome to Dr. Anil Kakodkar, Chancellor HBNI, Sri K. Nivas, Chairman, Council of Management and Secretary DE, Professor R.B. Grover, Professor Emeritus HBNI and Founder Director HBNI, Professor J.B. Joshi, Professor Emeritus HBNI, and other dignitaries in this council board, as well as in online mode, either on a WebEx or YouTube platform. I take this opportunity to introduce today's chief guest, Professor Indranil Manna. Professor Manna is J.C. Bose Fellow of DST. He is currently the Vice Chancellor of VIT Mesra, Ranchi. He obtained his Bachelor of Engineering degree from Calcutta University in 1983, followed by MTech from IIT Kanpur in 1984 and PhD from IIT Kharagpur in 1990. He is an educationist and material engineer with wide-ranging research interests. His studies on amorphous alumina alloys, laser surface engineering of steel, magnesium alumina alloys, boundary diffusion control phase transformations, and thermomagnetic properties of nano ferrofluids are highly cited. As a guest scientist, he visited different renowned institutions and universities abroad, like Max Planck Institute at Stuttgart, Liverpool University, and many others. He is a fellow of all National Academies of Sciences in India, as well as engineering. He is a recipient of the World Academy of Sciences Prize for Engineering Sciences in 2014 and was elected a Fellow of the World Academy of Sciences in 2015. He is also a member of the Asia Pacific Academy of Materials. He is the recipient of numerous awards. I will just name a few of them. The MRSI Medal in 2000, Pinani Gold Medal in 1999, G.D. Birla Gold Medal in 2008, AICTE Career Award for Young Teachers in 1995, INSA Medal for Young Scientists in 1992, and many others. He was felicitated by Minister of Peace with the Young Metallurgist in 1991, Metallurgist of the Year in 2002, National Metallurgist Award in 2018, and many more. He is the former President of Indian Institute of Metals and Vice President of Indian National Academy of Engineering. He served as a Director of CSIR, CCRI in Calcutta from 2010 to 2012 and Director IIT Kanpur from 2012 to 2017. Professor Manna is now the 14th President of INAE since January 1st, 2021. He is presently involved in making INAE a national agency for promoting engineering and technological self-reliance through translation research and innovation. I can talk about many awards and other things. I do not take more time of all of you, and I'm in between you and Professor Manna. May I request Professor Manna to deliver his talk? Professor Manna, please.
Thank you. Yeah, let me begin without wasting time. So thank you very much, Dr. Naik, and respected Dr. Kakodkar, Mr. Vyas, Chairman, Atomic Energy, Mr. Joshi, Dr. Grover, Dr. Vasudev Rao, and I can make out there are quite a few who actually are attending this occasion through the digital platform. So I should speak near the microphone, yeah, otherwise, is there, should be a digital pointer, right?
This microphone is for the meeting. This is for this hall only.
Okay, right. Yeah, okay. That's okay.
You can use up and down keys.
Right, okay. So thank you. At the very beginning, I would like to thank HBNI, the Vice Chancellor, the Chancellor, and all those associated with HBNI. This is an extremely coveted honor for me, and I remember all my life that I was invited to speak in this particular hall on an occasion dedicated to the memory of none other than Dr. Srikumar Banerjee. Scientists of my generation, particularly materials engineering community, we all used to look at him as an icon, as an epitome of scientific pursuit, to be a role model, basically. I mean, if anybody would like to emerge as a great scientist and be counted for very important contribution, he's the template. So I also have chosen a theme which was very core to his entire lifelong pursuits, very dear to the core of his heart, microstructure. And I would like to establish why microstructure is a very important component for designing of engineering materials, either for structural applications or functional applications. So I must upfront declare that I'm going to present most of the results which are not new, which are fairly old, maybe in some cases a couple of decades old. I actually have purposely chosen some results which actually was part of my PhD work and then subsequently my postdoctoral work in Max Planck Stuttgart, where Dr. Banerjee also worked. And that was actually the reason why I first came into touch with him. So I'll begin with certain fundamentals and which some of the experts in the audience might find very rudimentary. But I was given the impression by Dr. Vasudev Rao that I asked him a few times and he assured me that the audience are going to be mostly the scholars and students of HBNI. And I didn't expect the likes of Dr. Kakotkar and Mr. Vyas and Prasid Joshi and Dr. Grover to be here. But anyway, so for the timing, let me take the liberty of assuming that I'm addressing my second year materials engineering students, which I routinely do. I just would like to point out that these three items, basically moving boundary phase transformation, size-dependent allotropy of metals, and evolution of microstructure in laser materials processing, these are the three themes that I wish to elaborate upon. So at the beginning, of course, I would like to spend a couple of minutes remembering my own association with him and pay my most humble homage, who I consider, I just said, as truly an iconic figure. The first time Dr. Banerjee, I came across with Dr. Banerjee was in 87, 86, around that time. He came to metallurgy department in Kharagpur to give a lecture. That was a time when he actually got this Acta Metallurgica Best Paper Award. I mean, until that time, I don't think there was anybody in India who would have received that kind of an award from the materials engineering discipline. And ActaMet even today continues to be the Bible of the most coveted journal in our discipline. So we were all in awe, and that he spoke to me for a few minutes after the lecture separately was something which took me to the almost like over the moon. And the reason for that was I started working on moving boundary transformations, looking at the role of boundary diffusion control phase transformations, and that too not necessarily using microscopy as the tool, but resistivity as a tool, which was fairly unusual. And John Kahn and a few others reported, and but then Dr. Banerjee took interest because at that point of time, several of the colleagues in the department, senior colleagues, including my own supervisor, were his own contemporaries. So he came to know that Indranil, there's a new guy who is working on this. I was 24, 25-year-old. So he took me aside and then asked me a few questions, and I thought I could make him interested, so he remembered me. Then in 93, we started something called Congress of Metallurgical Professionals, which is essentially a platform for undergraduate students. Now, until then, there was no such event available in the country for undergraduate students to present their research. And in the very first occasion, somehow I probably was very persuasive, and being a young fellow, I took the liberty of reaching out, and people couldn't say no to me. So very many important people, you know, Dr. Shilbhadra Banerjee, then Dr. Banerjee, Srikumar Banerjee came. There were 4 or 5 very eminent people. And I was very surprised that he accepted the offer because he was already probably group director or something in BRC by then. And so he came down, and so in the interaction, he made it very clear that why he came down. He first said it's because of IIT Kharagpur, his alma mater. And then he said that in the country, we don't have a good mechanism of extracting research contributions from the undergraduate cadre. And that is something even today continues to be. Incidentally, none other than our present Prime Minister at the launch of Imprint mentioned this to us, that your best of the students are in your undergraduate departments. And somehow you fail to capitalize their talent pool, and you don't engage them much for research because they immediately leave and then they join the profession. So the fact remains that Dr. Banerjee also used that word. And then there was a special initiative from BRC to popularize directed energy beams, and one of them was electron beam. So BRNS gave a big project, probably about 1.5 to 2 crore project, and the machine was developed, built here, and then transferred, and Dr. Bapat and Dr. Ganpat and several of them were involved. They came and installed, and Dr. Banerjee came for the review meeting in VECC, and he said, "Why are you not the PI?" I said, "You know, so-and-so is very senior and is more of a welding man. I'm not truly a welding man or something." And he said that if anything goes wrong, I'll hold you responsible. So I knew that he's a very hard taskmaster, so I assured him. Then when we Institute of Metals, I mean, he was a former president, and he was the one who started saying that though we are an Institute of Metals, we have no animosity with materials. So why are we not talking about refractories, oxides, even polymers? But then the metallurgy community is very sensitive. They won't touch anything other than metals. But he was that way very progressive, and he realized that for any system development, we cannot be confined to only one set of materials and not others, or one approach or not others. So this approach of system engineering was also very key to his core. Then we proceeded, I came to CGCRI. That gave me another very major opportunity to interact with him very closely. In fact, I was very fortunate to have interacted with the likes of Shekhar Basu, and he was, Dr. Banerjee was already the director of BRC or something like that, and later on became chairman. And through him, actually, we almost entered into an agreement that Atomic Energy will fund a new research wing in CGCRI land. And he then, Minister of Science and Technology from Maharashtra, who was former chief minister, he came for those occasions, Prithviraj Chauhan. And so he convinced him, and everything was going in the right direction. But then we ended up into some land-related issue, registration-related. The land still belonged to Jadavpur University. We discovered, and then eventually I left, and that didn't materialize. But he was very passionate because of one single reason, that he only taught me that how important was it for CGCRI to have developed the radiation shielding window glass, the lead glass, and why it is important that even if a glass frit project for nuclear waste immobilization, even if it is just a small output project-wise, but still why it was so important. And then he also very wholeheartedly supported the laser glass project. So all these specialty glass projects, and then he would, in the council meeting, amazingly, he would spend 2 hours, 3 hours, even after the meeting, and talking to individual scientists and pointing out where something is going wrong and what actually needs to be done to. And he was very clear about certain things, that your product has to be of international standard. You cannot say that this is done by CGCRI, so that Atomic Energy should accept that. So you have to fulfill all those and tell us what needs to be done to do that. So one other, I realized later on that why he was always willing to come, it was not always CGCRI, it was also partly Ramakrishna Mission. Because in the evenings, he would quietly slip out and say that, I'm going to go and spend some 1 hour or so talking to, and the Maharaja of Ramakrishna Missions, all of them were so fond of him, because when he enters Ramakrishna Mission, he was just a student. And though he was so learned and erudite, but with Maharajas, I mean, somehow I've seen him being very, very a devoted soul. Similarly, he would, every time he comes to Calcutta, he'd receive so many awards or something or other. And I used to follow him, and he used to feel embarrassed that something is going on and so on. But he would set aside at the end of the meeting, and then immediately pick up and straight away come to the point that this needs to be done, that needs to be done, or something. Then I moved to IIT Kanpur, and it gave me an opportunity to start this very ambitious project called Imprint, which many of you know, Dr. Kakurkar was part of it. And to my surprise, he was already a very big man by any means of imagination in the country. He was chairman Atomic Energy, earlier director bar. he accepted my request to be the chair of the advanced materials domain. We had 10 domains in imprint, and he was the National Committee chair for the advanced materials domain, both for imprint 1 and imprint 2. Dr. Kakutkar was in the Apex committee. And when he sits for a review, he did exactly what Mr. Vyas was telling us, that he would go exactly, not that he would like to denounce somebody, but he was very ruthless in pointing out where lies the mistake or where we are making a mistake. Similarly, for one very young assistant professor, he prevailed upon us to give 5 crore. And out of that 5 crore, 3 crore was exactly for this translation to tons level, which Dr. Kakutkar was saying. With Midhani, the new titanium alloy was melted and cast and then forged, and because those facilities don't exist elsewhere. And to be able to convince Midhani to go to that level, we had to give large amount of money. So he was very supportive for such initiatives. And 2018, I finished my Kanpur tenure. He was made, by the way, he was chairman BOG IIT Kharagpur. But I also used to consult him very often from Kanpur. He was also our visitors nominee for some of the departments. And so 2018, January, he came to Kharagpur to give series of lectures because he was given some special chair or something for IIT Kharagpur. His term ended as chairman BOG. So January 28th or so was the Saraswati Puja. And somehow, some of us coming from the Bengali community, we are very devoted to Saraswati Puja. So he tells me, Indranil, tomorrow is Saraswati Puja. Do you do something here? I said, oh, of course. In IIT Kharagpur, there are many places they celebrate or something, but we do small way in my own home. And he and Mrs. Banerjee, both of them came and spent the whole morning and joining us for the Saraswati Puja or something. So all I'm trying to say is that, I think Dr. Kakutkar also mentioned, the humility and the intensity, both a very rare combination with which he conducted himself throughout his life, was a lesson to be learned. He was never imposing type. He was very accessible, but he was very firm. And in fact, all throughout my interaction, I'm going to talk about discontinuous precipitation. He would always, every time I mention, he says, no, this is wrong. This discontinuous, actually, the word actually contradicts J.W. Christian's classification of phase transformation. You call it cellular, you call it something else, but don't call it discontinuous. I said, Dr. Banerjee, this is an established terminology in the whole of the literature. I have 2 reviews written, and there are books which mention my work or some others. Still, he would say that he will stick to that. So difficult to convince him, but at the same time, he was very, encouraging type. I would always look at the youngsters and try to encourage them. So it's a real shock when we heard that he is no more. And that's why I say that to be given this platform to speak about my perception about microstructure, I consider this to be a great honor, which I'll always remember in my life. So thanks again to HPMI. So let me start my discourse by showing this very colorful collage. If you look at, I've picked up some very odd and randomly chosen components of metals, ceramics, semiconductors, polymers. When we look at the right side of the collage of these systems called an automobile or a railway wagon, then this fighter aircraft or a ocean liner, nobody can say that these machines or systems are created only by the polymer engineer, only by the ceramic engineer. Nobody can say that for developing this system, I need only ceramics and not metals, or I need only metals and not polymers. So basically, at the end of the day, the society demands the best solution at the cheapest and most sustainable rate. Doesn't matter whether you use semiconductor or polymer or something, I want the best product at the cheapest price and which is sustainable and acceptable. So similarly, if you look at this, the modern airliner, I mean, carrying some 500 passengers in 14 hours, you reach from New Delhi to New York. Can anybody say that only an aeronautical engineer or mechanical engineer has made it? Actually, it goes beyond engineering. I mean, you need even input from economics, from humanities, from various other disciplines. So the first word that I would like to convey is that engineering is all about providing solution and answers to the society's aspiration. And the society doesn't care whether you need one type of an engineer or another type of a material, or you need something beyond. It has to be sustainable. And in order to do that, we make a common mistake, particularly at the design table, to go by numbers. Say, for example, somebody says that for this material, I need so much of yield strength or so much of fatigue strength or so much of ductility. And we look at the data book, handbook, and say that, okay, this percentage or this megapascal or this kilojoules. So I pick up this material. Little do we understand that this description of material by numbers, quantitative description, actually is subject to a variation over a wide range. The same material can give you 500 megapascal, 700 megapascal, or even 200 megapascal. The same material can fail at only 200 degrees centigrade, but can work at 500 degrees centigrade. So the differences, irrespective of the composition or for a given alloy, the differences are made by a composite conception or paradigm called microstructure. And in order to understand that microstructure, we basically have to start from the fundamentals. But that fundamentals that we begin with is not related to the single atom. So single atom, so interatomic forces or single atom or intraatomic forces or intraatomic particles or subatomic particles, that's the realm of the physicists and the chemists or the basic scientists. As materials engineers or as engineers, we deal with the aggregate. And this aggregate manifests itself in two possible ways. One is one where I have periodicity. I have periodicity along X, along Y, along Z in all three Cartesian coordinate system, or I don't have that periodicity. At the most, I have some close neighbor configurations and sort of short range order, and I call that non-periodic, non-crystalline or amorphous. So either crystalline or amorphous are the two basic manifestations of the solids that we deal with for any amount of engineering applications. Now, if I for a while spread all possible materials in front of me, and I impose only one restriction, they have to be pure. So there is no mixture, they're all pure. Then essentially I'm dealing with only three kinds of fundamental materials in terms of one single attribute, and that is bonding characteristics. So whether something is hard or soft or conducting or non-conducting or very transparent or opaque, all properties put together, I can distribute and I can classify in terms of three main categories in pure form. Whether they enjoy ionic bonding, at least predominantly, whether they enjoy covalent bonding, or whether they enjoy metallic bonding. And accordingly, I say the ceramic materials, including semiconductors, I say polymeric materials, we enjoy the covalent bonding, and I say metallic materials, which enjoy the metallic bonding. And accordingly, if you look at the bottom of the slide, the attributes, if you compare, for ionic bonded materials, you expect large melting temperature, large elastic modulus, and very small coefficient of thermal expansion. For polymers, you see the opposite. You seem to expect low or practically very low melting or softening temperature, fairly low elastic modulus, and variable coefficient of thermal expansion. For metals, you expect moderate to high melting temperature, elastic modulus, or coefficient of thermal expansion. So in terms of three attributes, you realize that the variations could be very large depending on what is the fundamental of the bonding characteristic that make up these aggregates in three dimensions. So host of these properties which come because of these classes of materials, obviously we are not going to spend time on that. Now, so as I said that, for example, if you look at silica, when you talk of silica as quartz, then it is completely crystalline. I have three-dimensional periodicity. So the silicate network is so arranged that the silicate is located at very specific predetermined repetitive positions. The same silicate can also exist in completely non-crystalline form, which is what we have in the window glasses, and they can manifest very different set of properties. So apart from viscosity, this periodicity also is one of the biggest attributes why quartz is quartz and why amorphous silica has a different set of properties. So I see them as crystalline or non-crystalline. What is the way to distinguish? Very simple, I'll go to some diffraction analysis, which essentially allows me to do constructive interference. And if I actually am able to match the repeat distance of my species, be it ion or molecule or atom, with the repeat distance or the wavelength of the incoming electromagnetic radiation, then I see such fingerprint of crystallinity. So I see a diffraction pattern with very specific peaks with large intensity at some periodic interval. Otherwise, if it's aperiodic, then I see a very large halo. And if it's atomic and monoatomic gases, then actually the intensity is constantly decreasing. So just like I identify a man by the fingerprint, looking at these diffraction patterns, I know whether it is crystalline or non-crystalline. And furthermore, I can actually identify and determine what kind of a crystal structure I have through certain other descriptions. So for that, I resort to crystallography. And there I actually take into account the smallest building block of that, which is called the unit cell. And using that unit cell, I can straight away declare that any amount of either simplest or the most complex crystal structures will definitely be related to one of these 14 Bravais lattices. So that's sacrosanct. And a very standard question I ask my students that how many Bravais lattices? 14. How many crystal structures? They'll scratch their head and somebody will say some number or other. I said infinite. So this is where the supremacy of nature lies. The template is only 14, but actually the number of variations possible out of these 14 templates is actually infinite. And this is where we have to learn from the nature. But the good thing about the metallurgists is that we don't have to deal with very, very complex structures. We are happy dealing with merely simple face-centered cubic, hexagonal close pack, and body-centered cubic, or some such very simple structures, because more than 80% of the metals belong to such simple structures. So the first part, these are imaginary, and the real one is the crystal structure. And that is where all the intricacies of structural design of materials lie. We also deal with polymers. In fact, there's an enormous sense of application. The interesting thing is that though polymer primarily is non-crystalline, but it is always a possibility of crystallization of polymer, and that's how you actually can improve the creep strength or many of the other limitations that we generally come across. And today we talk about flexible electronics, and so we functionalize and we bring in certain structural characteristics of polymer because of which they actually can compete with semiconductors. So there's a lot to be learned, and so this is also another important classes of materials. Now, when we describe all these, we tend to believe as if everything is ideal, everything is perfect. It's not. In fact, all the properties that we deal with in solids are more influenced by the defects than the periodic structure itself. So these defects can be manifested in terms of in crystalline material, in terms of 0 dimension, in 1 dimension, 2 dimension, or 3 dimension. Accordingly, we have vacancies, interstitial, substitutional, and if it's a polar compound, then we have Schottky or Frenkel defect and various other complexes. But in case of metallic materials, we are more keen on understanding the dislocation dynamics. So it is not enough that if we have dislocation, a very common question we ask to the students is that sodium chloride is actually FCC, rather than this. It has dislocations, yet sodium chloride is extremely brittle. It doesn't show the same ductility as aluminum or copper or any other FCC metal. Why not? It's because of the polarity. So dislocation, presence, density, population, and its dynamics determine the relative plasticity or strength of the material. So in very simple terms, if dislocations move, the material is ductile. If the dislocations are immobilized, the material is strong. So the same material can be, after annealing, very soft. The same material after certain phase transformation or treatments can be made very hard and strong. And that is where the differences in the microstructure come handy. So in terms of defects, we also have the 2-dimensional defects called the boundaries, grain and phase boundaries. ring boundaries, and three-dimensional defects, for example, the inclusions or any other foreign particles. How do we deal with materials? These are the things, any materials, metallurgy or manufacturing or mechanical, all of us get exposed to melting casting, continuous casting, heat treatment, drawing, extrusion. So these are the fundamental unit processes through which I deal with metals, powders, or even polymers, even ceramics, all kind of engineering solids to give a final shape or dimension that I want. Now, when I approach such processes, I have to bear in mind two important body of knowledge. One is the thermodynamic angle, which sets certain constraints in terms of equilibrium solubility. Say, for example, you take a glass of water and you add sugar, there's a limit until which you can add sugar. You raise the temperature, you can add more sugar. You lower the temperature, excess sugar comes out as precipitates, as crystals. The same thing happens in case of solid materials also. And this behavior in terms of whether a component one is going to get dissolved in two, to what extent, at what temperature, what is the limit, all these details are embodied in a body of knowledge called phase diagrams. So that's thermodynamic constraint. The next part, the next constraint comes from the kinetic part, that when I want to make a change, whatever I have, I'm not happy, I want to improve the properties, so I want to bring in some changes. So changes means the aggregate that I have in terms of maybe only A type of atoms or AB or ABC or ABT or whatever, I need some changes. In order to make some changes, the constituent atoms have to move, have to change their positions, take up new positions, create a new phase or different shape, morphology, and so on. So I need atoms to move. And these movements are typically diffusion or thermally activated process. So there the diffusivity is a function of temperature. So I cannot, even if I want, I cannot complete a process within 10 minutes if the diffusion coefficient is not helpful to me. So I have to then design the process such a way that, and mostly in metals we deal with solid state, unlike in the chemical processes where actually the liquid state also comes. Of course, we have liquid state, but most of the solid designs are based in solid state divisional control. So one has to keep into mind these two major constraints in order to design. And in many such cases, materials people would always like to break away from these constraints. And that's where we go for so-called non-equilibrium processing. That means I want to do something and end up with something which is going to give me properties which are different than what is possible by equilibrium thermodynamics or equilibrium kinetics. So what I do is I either cool very fast or deform very fast or subject to some very high energy processes or give extreme amount of strain and strain rate. So these are the tools and approaches by which I can break away from equilibrium and end up with something which either can be called a metastable process or an even unstable process. So when it is unstable, it is something which is bound to change very soon. But when it is metastable, then you actually can play with the kinetic parameters and make sure that it doesn't transform until you raise the temperature or give some additional pressure or something. So which is not stable at high temperature, can be stable at room temperature. And you take the advantage of that and derive some new properties. And for example, steel, which we always use all the time, this is also a very common question to the students that is steel a completely an equilibrium material? The answer is actually no. Because in steel at room temperature, we have perlite. Perlite has cementite. And the equilibrium phase in iron, in fact, we say iron carbon system, it's actually iron cementite system, which is a metastable system. The true equilibrium system is iron carbon or iron graphite. So actually, if you allow sufficient time at high temperature and cool very slowly, then there'll be no cementite. Cementite will gradually decompose to graphite. So, but we use steel, all the bridges, all the buildings, everything is made out of steel and at room temperature. So what does it mean? We have a lot of danger from them? The answer is no. Because in order to change from cementite to graphite, the diffusion coefficient that you have at room temperature is such that it will never change even in a millennium. So you end up with this. In fact, we all extol these Damascus sword or our own Indian version of these rustless steel and so on. that also takes care of that. I mean, I wonder how did someone at that age actually could understand that you reduce iron oxide by graphitic route by carbon using charcoal or something, and you process it at such a low temperature that that graphite doesn't combine with iron and form cementite. So those swords or those iron pillars actually has pure iron and sulfur and carbon in solid solution. So it is for this reason there is no corrosion, because you are dealing with a single phase structure. For corrosion, you need two phases. One will be anodic. Dr. Vasudev knows better than I do. You need an anodic phase. There's no anodic phase there because it's a single phase structure. And they process it such a temperature that they retain the graphite at that temperature. And it didn't cause any galvanic cell in the structure. Anyway, so these are the non-equilibrium processes by which you can develop. So the question is, how does the microstructure evolve? Where does it start? What is the microstructure? What is the origin? If you look at this view graph here, so this is the liquid. Let's say the gray area is liquid. And these are a few tiny atoms which are coming together. So initially just a few, then a few more. The size increases. So the size will be sustainable only when you cross the critical radius size. So you have to attain a critical size so that you balance the increase in the budget because of creation of interfaces, the so-called interfacial Gibbs energy. You compensate compensate for it sufficiently by reduction in Gibbs energy through the chemical means or the volume free energy. So I have to strike a balance between increase in Gibbs energy due to creation of new interfaces, boundaries, by decreasing Gibbs energy by conversion to a more stable state. So in this balance, whenever I attain a critical size, then I say the nucleus is stable. And then onwards, the nucleus grows and I have growth stage. So initially just randomly created locations, and usually this is heterogeneous. At some preferred sites they form, and then they grow, and they continue to grow, and eventually they consume the last drop of liquid. When you have no liquid left, then you have all solids and these boundaries. So these are the grain boundaries. And the rest is all, there's a single phase, so all single crystal, single phase polycrystalline aggregate. And when we go under the microscope, then we see very nice, I've taken again random pictures, they have nothing to do with each other. But look at the nice varieties that you can produce. And this is how we get very enamored with the romance of microstructure. Very acicular structure, needle-like structure, rod-like structure, lamellar structure, like the curtains hanging on the windows, or the globular structures, or cuboidal structures. How do they evolve? Who dictates them? Nature. By what means? By surface energy. So basically, once I have nucleated, the shape that I take for a given system will be primarily dictated by the surface energy. And if I can play with the surface energy, I can play with these shapes. If I can play with the growth stage, then I can also allow something to grow bigger or smaller. If I create more nuclei, then I have smaller entity. If I allow only a smaller number of nuclei, then I have bigger sizes. And in fact, in the limit, if I allow only one nucleus to grow, then I have a single crystal. And that's how I produce all my semiconductors, silicon semiconductors, or even turbine blades of few meters height. So I have to understand the basics of the evolution of the microstructure, and then how do I strengthen them? I'm referring primarily to the structural applications for mechanical behavior, but it can also be for functional applications. So for example, if I want to make the tea taste sweeter, what do? I add more sugar. If I want to make the alloy stronger, I add more solute atoms and make the life of dislocations more difficult to move. So I can do solid solution strengthening. I can add dispersion hardening. In fact, Dr. Saibaba was talking, NFC was the place where the country developed the ODS alloy, oxide dispersion strengthened superalloys. So that is the strategy, that you disperse precipitates, particles, which are insoluble. So difference between solid solution or precipitation hardening and dispersion hardening is that in one case, you have solubility at high temperature, they dissolve, you add more sugar, they dissolve, then you cool down, the sugar comes out as crystals. So these are your precipitates. In the other case, the dispersoids are like, some dirt or saw or silica particles floating in water. They'll never go into solution. Yet they can pose problem to dislocation movement, and that's how you produce. So they're very useful for high temperature applications. Then, of course, we have grain size strengthening or martensitic strengthening and so on. So these are the basic strategies by which we proceed. So this was the fundamental part of it. So having understood that solids can be crystalline or non-crystalline, and we try to understand the structure and the microstructural evolution through various techniques. And now I'm going to take up these one or two examples. And Dr. Vasudeva, you should tell me when I should stop. I can stop at 10. So, 15-20. Right. So basically imagine that you have taken an alloy of this composition X naught. And if you equilibrate at this temperature T1, you have a single phase microstructure. And when you cool down, like I said, the sugar crystals will precipitate out. Similarly, some precipitation happens. And this precipitation can happen through a volume diffusion control mechanism where I have precipitates all over distributed. I can also have a very special mechanism where precipitation happens against this moving boundary. And these are called moving boundary transformations. Very rare, but it does happen, and it has a lot of bearing on some very specific alloys, including superalloys. In most of the cases, people don't want moving boundary transformations, but as scientists and engineers, we need to understand the mechanisms, the basics of it, so that either we use it or don't use it, or we prevent it. So, for example, steel, the entire pearlitic microstructure, the eutectoid transformation, is a moving boundary transformation. But the difference is steel has interstitial solid solution, small particles, small carbon atoms, which is very different in mechanism than all these brass or bronze or all superalloys or substitutional alloys. So this, what I started with my PhD work, and the theme that I actually addressed to was that what was the mechanism and what actually can one do useful from this. So continuous and so-called discontinuous precipitation comparison. So just few microstructures to tell you that it's indeed very, very fascinating. So you see here what you're doing is, what you're seeing is, if you have such very fine lamellar aggregate, gradually it can start coarsening. Now when such coarsening happens, that strength decreases. So in most of the cases, you don't want such thing to happen. And in my work, I was able to show that such kind of coarsening can happen, not necessarily from the grain boundaries, even from phase boundaries. So similar things can happen by this. So when the boundary moves, let's say in this case, when the boundary moves in this direction, then one coarsening transformation starts. But when the boundary recedes in the opposite direction, that means the direction from which it started, then you actually see dissolution. So that means it is just like a beach mark in the sea beaches. You see the water encroaches into the sea beach, the front increases, and then it recedes. The same way, in solid state, a boundary can move, cause precipitation, but if you raise the temperature, then the same boundary can recede and dissolve. So in some special cases, you can even see diffusion occurring and diffusion driving into formation of solid solutions with such faceted forms, just like the pyramids. And this, you see the difference here is that this pyramidal structure shows that the boundary configuration here has a very specific surface energy, very different than random grain boundaries. Because of the faceting, you can very well make out that it has fairly low energy configuration, and because of which it has preference to only certain angles. So these are the fundamental aspects. And the funny thing is that if you look at, say, for example, this structure, you can easily make out that statistically they maintain the same interlamellar spacing. How do they do that? How does nature ensure that when the colony grows, they maintain exactly the same interlamellar spacing? And please remember, this spacing has a lot of bearing on the mechanical properties. So in order to understand, you have to see that there are two possible mechanisms. One, that you continue to nucleate on the boundaries at regular intervals, or you allow the boundary to move and the lamellar behind to bifurcate into two. So if you have a planar front, then I can afford to have 1, 2, 3 at regular intervals. If I have a non-planar or a curved front, then I cannot maintain the same way. So in that case, I allow one lamellae which was growing to bifurcate into two and maintain the same distance. Why is it so important to maintain the same distance? because the boundary is the feeder channel for the solute atoms. And in order to feed at regular interval, I have to maintain the same distance apart. So this is how the process continues. And in fact, funny thing is that I also was able to show that you can form such fancy structure. So imagine just like a star. You have three boundaries meeting at a triple point, and all three of them can grow in different directions. What determines which way it should grow? Then I went into another very interesting phenomenon, and I realized that the same boundary, depending on the boundary configuration and the corresponding energy, can either move, say, upward or downward, depending on the local curvature. So that if the local curvature is convex forward, then it will move in one direction. If it is convex downward, then it moves in the other direction. So the energy also is related to the curvature. In other words, curvature affects the energy. So effectively the energy, but that can come through this. Then I showed that normally in metallurgy circle, if you say that twin boundary is a heterogeneous site for nucleation, nobody would believe. And here is one such example, that on a twin boundary, I could show that this kind of a transformation could happen. What was the reason? Boundary transformation. So the boundary itself can transform from low energy to high energy configuration and be eligible for nucleation of such transformation. So that means the microstructure that I'm dealing with now is not sacrosanct. It can change on its own in course of time if it's exposed to high temperature. Then comes the fact that here was a single crystal. You see, all are black, no precipitation. And then what I did, I put intentionally an indentation, plastic deformation. And plastic deformation at high temperature creates its own recrystallized boundaries. And these recrystallized boundaries now become agencies for boundary growth. So now I have precipitation only around the indentation mark. So that means I can create heterogeneous sites and make a specific transformation possible from that site. So various other facets I'll cross that. So what was the utility? And this is where I had a lot of interaction with Dr. Banerjee. So I told him that this discontinuous precipitation actually is a good mechanism of measuring grain boundary diffusivity. And it's a triple product. In fact, diffusion community would immediately understand that if you only talk of diffusivity in a polycrystalline aggregate, it is not the complete information, because the diffusion, depending on the prior history, can also be different in rate. So then you have to come out with something which is normalized. So what are the normalization factors? One is S, which is segregation factor, that if there's solute segregation, it takes care of that. Then D, delta. Delta is the boundary thickness. So when you talk of diffusion coefficient of boundaries, then you talk in terms of a triple product, S delta dB. And using these kinetic models, it's not me alone, there were many other researchers, but at least I had the satisfaction of being able to report boundary diffusion coefficient in some of the systems where no boundary diffusion coefficient data was available. And Dr. Banerjee took note of that, and he said, this is something great, so you should pursue this. In fact, he was a little unhappy when I moved to laser. He said, why are you leaving that field? There's so much to be done or something. We all want to, Professor Joshi, with due regards, we have to publish now, otherwise academics have no life. And it was becoming very difficult to publish in this field because it was already kind of getting older and getting saturated. Of course, there are still a lot of things to be done. So what is interesting here is that this is a data which is in situ data. Now, we tend to believe that when the boundary moves, it moves continuously. It doesn't. It undergoes actually a stop and go mechanism. So this is in situ data, where this is not my data. Someone showed actually the boundary moves for a while, exhausts the driving force available, waits for some more solute atoms to build up in front so that there is a potential difference, chemical potential difference, and then again starts moving. But when you do macroscopic observations at time 1 hour, at 2 hour, at 4 hour or something, then you plot the data and see a continuous curve. But actually inside the continuous curve, you have steps. Now, these are things which are very important because if you're doing failure analysis, at some point there is a sudden burst. Why did that sudden burst happen? Then locally, it could be possible that the local thermodynamic conditions varied to such an extent that there was a sudden burst. Now, the biggest contribution, in my opinion, which I take biggest satisfaction, is that we were the first one to report that the boundary mechanism, movement mechanism, and diffusion coefficient is identical between what you measure from grain boundaries and phase boundaries. So that means I had to create a same, in order to make people convinced. What I did was, instead of the red alloy, I chose the blue alloy. And I did parallel experiments. With the red alloy, metallurgists would understand that I have only grain boundaries. With blue alloy, I have both alpha and delta grains. So that means I have alpha alpha, delta delta, and alpha delta boundaries. That means I have grain boundaries and phase boundaries. And I measure very meticulously such kinetics of the process, both from phase boundaries and grain boundaries. And then I showed that they are identical. And this paper actually received a lot of attention, and Professor Ranganathan of ISA Bangalore was very, very happy to see these results. So I'll come to the next. So this was all about my initial foray with physical metallurgy, microstructure, grain boundaries. And all to my satisfaction, all I could do was to actually understand not only the mechanism, but also see the potential applications. But as I said right in the beginning, today I'm not talking about any translation or application. I'm only talking about fundamental science. The second part is allotropy or polymorphism. And that's also something, again, something if you ask a student, why is steel so great? I mean, all metallurgists, the metallurgists are born and they die with steel. Everything is steel. So why is steel so important? And in my opinion, I mean, more than 95% of the students, even some of the senior ones, won't be able to give the right answer. And it all is because of a very strange phenomenon that nature has created only in iron and a few other such transition metals, which is basically exchange interaction. The iron is ferromagnetic at room temperature. Because of that, iron is steel with carbon because of that. And what is it? If you look at all metals, the general rule nature imposes is that if you start at high temperature, the entropy contribution is higher. At lower temperature, enthalpy takes over. So that's why you would have more close-packed structures at room temperature and less close-packed structures at high temperature. So the BCC and other varieties are at high temperature. Look at titanium, look at cobalt, look at all other standard metals. You'll all find that the BCC or the loosely packed structures are stable at high temperature. At room temperature, you have either FCC or HCC. Steel is an exception. Iron is an exception. Why does it happen? Because of the exchange interaction, because of the 3D 4S interband transition possibility. So it goes to a hybridized state, neither 3D nor 4S, and it starts exchanging even before filling up either 3D or 4S. And because of that, we have the possibility. Dr. Grover must be, he's an expert in solid state, so he knows. So the magnetic properties, the entire either ferromagnetism, paramagnetism, or in some rare cases diamagnetism, all we try to explain through these fundamentals of exchange interaction and magnetic properties. Iron is the only element which starts with delta ferrite BCC, then either austenite or face-centered variety of gamma iron, and then again it changes to BCC iron. And until room temperature, it's BCC. It is because of that we see eutectoid transformation. And why I'm spending a minute on that is, when I started publishing in this recently, not only Srikumar Banerjee, even Rajarshi also has some publications in that, and I'll come to that in a minute. Very interesting story. So Dr. Banerjee also was initially very skeptic at some of the results. He said, I was very much, because every journal I send, it gets rejected. But I was convinced that no, there is an interesting science in it. So the point here is that you see this allotropic changes of delta to gamma to beta to alpha as a function of temperature. What we reported was as a function of pressure, and that too pressure from within, not macroscopic pressure from outside, pressure from within. And where it's coming from, I'll come in a minute. So, and this is where Dr. Banerjee actually pointed out that, you see eutectoid transformation in steel you see detector transformation in zirconium. Honestly speaking, until he explained to me, I wasn't too aware of zirconium. In fact, our Sai Baba was talking about zirconium, niobium, and so on. Fantastic metallurgy there. Fantastic metallurgy, because zirconium is very similar to iron. Very similar phase diagram. And very similar eutectoid transformations, very similar martensitic transformations, ordering transformations, very many things in common. The only difference is that all zirconium alloy, like any non-ferrous alloy, are substitutional solid solutions, whereas steel, iron, is essentially interstitial solid solution. Okay. So, I mean, leaving aside all this, you have to believe me that I used mechanical alloying as my tool, and I was able to reduce the crystallite size. And the thesis that I propose here is that if you start, imagine you have a volume and you have 100 atoms, 100 grains. Now, if you make it truly small, truly nanocrystalline, I mean, maybe 10, 20 nanometer. So that means now you have, instead of 100, you have, let's say, 1,000,000 crystallites. So no change in composition, no change in crystal structure, only change in the domain, the grain size, the crystallite size. So that makes a lot of difference to the boundary configuration. In fact, this is what Professor Gleiter proposed, and of course, a lot of modifications happen. So theoretically, one can show that actually the free volume per atom, if it is more than 100 nanometer, is negligible. But the same configuration, when it is less than 10 or 20 nanometer, the free volume per atom increases exponentially. And in fact, if you reduce, so imagine you have a crystalline material, you start reducing the crystallite size. So from 1 micron, you make it 100 nanometer, 10 nanometer, now make it 1 nanometer. How many atoms do you have? Few tens of an atom. Is it still crystalline? Nobody can prove. So effectively, one can argue that you can actually have a crystalline to non-crystalline transition because of only size reduction. So with this, you also have created a pressure within, which we call negative hydrostatic pressure. So you have a volume and you have pressure which is exerted from the core towards the periphery, which is trying to push the atoms away and expand. In fact, that is well established that there is a tendency of expansion, that lattice parameters expand and so on. And we actually came up with a theory that when the negative hydrostatic pressure numerically is equal to the bulk modulus, then you see a collapse and it becomes non-crystalline. So using this, we were able to show, we took titanium, we all know at room temperature is HCP, and we were able to prove that after 150 hours of milling in very low intensity, it gives you a signature, diffraction signature, which is FCC. If you go for high energy milling, then in 30 hours, you convert everything to FCC. Titanium FCC at room temperature was not known. The only person who actually reported this kind of a crystallographic change was a celebrity, and I mean, is a celebrity, and everybody would recognize the name is Dan Shechtman, the person who reported and got Nobel Prize for reporting quasicrystal. I was fortunate enough in 2002 or 3 to visit Israel, Technion, and I had a good friend and he took me to. Dan Shechtman was already a renowned professor, but nowhere compared to as famous as Nobel laureate. But he didn't have tons of publication or something. That's Israel, because he was very good in some mechanical processing of materials. I mean, very well known. He even had an industry to him by then. So I managed to go and talk to him and I showed my result. He was very happy. He said, oh, you have reported this? He reported on thin film, not by mechanical alloying, on mechanical deformation process. He showed by reducing the crystallite size by vapor deposition, thin films, he reported such FCC transition, HCP to FCC transition. And he published in an obscure journal. He said, nobody accepted my results, so I ended up publishing there. I said, Professor Shechtman, I'm a very nagging person. That time I published one and then subsequently I published more. So I was very fortunate. And in fact, that gave me an opportunity. After he got Nobel Prize, I wrote to him. He replied after 2 months that I was so busy or something, but he remembered. So basically all I'm saying is that against the nature doesn't allow you to have FCC titanium at room temperature, but we could make it a metastable structure by way of specific processing. In fact, a lot of results, I'll skip all those just to prove that. In fact, I took the help of atomic energy to a large extent in this kind of a work through a Saha Institute of Nuclear Physics. The Ghosh Roys, the husband and wife team, and Nambisan helped me with all these positron annihilation spectroscopy. I mean, all of you are aware, you're all atomic energy people, that positron is actually the most authentic probe for vacancy detection in solid state matrix. Because positron is a positively charged electron, so if you have a vacancy, you have a different environment, and positron goes and immediately captures that. It annihilates and the intensity you capture. So from that, you can count the density of vacancies and their distribution and so on. So I'll keep all these results. In fact, it also allowed us to show that it goes to a saturation, the positron lifetime goes to a saturation when the crystallite size stops decreasing anymore, because there's a limit to which you can reduce, not beyond. So through some equation of state analysis we carried out, we were able to calculate the negative hydrostatic pressure, and we calculated separately the strain rate and so on. I'll skip that. We showed similar results in zirconium. In fact, 3 early transition metals, titanium, zirconium, niobium. And please remember, 2 of them are HCP at room temperature, 1 of them is BCC at room temperature. In all these cases, so the question many reviewers asked that why should they prefer to be FCC? And the persistent comment from the referees was that it is impurity effect, it is something. So I had to do a lot and try. So then they said, can you try this in alloys? So I went back and started doing it with alloys. And we showed that in titanium zirconium alloys also, we have similar results, similar signatures. So very elaborate calculations and so on. So and then one other very consistent thing was, and Dr. Banerjee also said that this is a very pertinent question and you must probe it. People said hydride. And we all know titanium, zirconium are very hungry for hydrogen, and hydrides are FCC. So a lot of reviewers say this hydride. So we showed our result that you hydride intentionally and dehydride. So you hydrogenate and dehydrogenate, and then you see that there's a difference. So you prove that it is not hydride. Then somebody said that, why do you say allotropy? It is polymorphism, because by jargon, by our science, we say that anything which is reversible is allotropy, which is irreversible is polymorphism. This is kind of well accepted. Then I had to show that it is reversible. I had to show by annealing, you lose those peaks. So we and then went into the phase diagrams and showed that the amount of these impurities like carbon, nitrogen, or oxygen, the amount of them you need to have single phase FCC is way too high compared to what we have. We have impurity, but in ppm level, maybe few atomic percentages, but not 30 atomic percent or 40 atomic percent, because the phases are in the middle of the phase diagram. So finally, and then we showed in zirconium and all these analysis, I'll skip that. So this is the significance of the results. So we were able to show that, science you pursue know why. You don't care whether it is going to be used right tomorrow, but if there's something new, fundamentally new, you're very excited. And that's what we showed, that it is not by temperature alone, even by pressure, and that too from pressure within, because of structural size reduction, you can see such structural transformations. And 10 years after we reported our results, a group came and reported, and they referred to our paper and said that if you just, they say that they are able to see a higher amount of ductility in FCC titanium than HCP titanium. So I never had a clue, but now I jumped up, I said, oh, look, there is an application. If you can convert HCP to FCC, we all know that HCP has limited slip system, so ductility is not as good as FCC. So if you can convert anything to FCC at room temperature, the HCP metals, I'm just kind of, this is a wild imagination. If I can do that, then I can claim that there is an application. Then I can make things more deformable. And this is exactly what was commented by the other researchers in 2016. And then I quoted this thing just to impress you all. Polymorphism or allotropy is an established science, not now, for 100 years. But when this was first proposed, it was doubted by a scientist of the reputation of Ledebour, after whose name Ledeburite is, is an established phase aggregate in cast iron. In cast iron or in iron carbon system, if you have a liquid to solid transformation, then you don't first see the eutectoid. First you see eutectic, and the eutectic transformation product is called Ledeburite. It is named after that German scientist, Ledebour. And Ledebour thought that allotropy is too artificial to be true. But it was proven to be correct, right? So this is the power of science, that it doesn't, wait for an individual's opinion. Eventually, if you have evidences and if you can prove, then it gets accepted. So I'll end up now just saying that, so this is titanium alloy used in the compressor part of the turbine engine. And we showed that if you alloy with silicon to some extent, you produce some silicides, and you improve the oxidation resistance. This is reported, well established. What is interesting and why I'm pointing out is the composition that we chose is in the hypoeutectic zone. The microstructure that we have is in the hypereutectic zone. The metallurgists would understand this easily. How can you have hypoeutectic composition and get hypereutectic microstructure? It's purely because of metastability. So in laser processing, you have cooling rate which is in excess of 10 raised to 5, 10 raised to 6 Kelvin per second. So you have such deep undercooling that actually the composition remains where it is, but the diagram itself has shifted so that hypo has become hyper. Similarly, with magnesium alloy, we showed that just by surface melting, you can convert this microstructure into this refined microstructure. And what is the advantage? The advantage is it is good both for against corrosion resistance and strength. Why? Grain size refinement. And the crystallite size now has become so small that you cannot form a galvanic cell. The anode cathode distance is now so short that there is no galvanic cell formation. So overall corrosion resistance of the property improves. Similarly, but laser is not panacea. So even bulk metallic glass, which at room temperature is glass, cannot be written even by laser processing. So fast cooling alone is not the answer. So you have to understand why not? Because you have in bulk metallic glass, you have chromium, iron on one hand, molybdenum on one hand. On the other hand, you have boron and carbon, interstitial atoms, very fast moving, very high diffusivity, and large difference in melting and boiling temperatures. So as soon as a melt form, even if it is 1 micrometer cube, within that, there is immediate phase separation or solute separation. So what was a single phase now is phase separated. So you end up getting all these peaks and all these phases. So, I mean, one has to understand that. And then in some other case, we proved that even in solid liquid transformation, which is common in case of laser processing, one can form martensite in some of the alloy steels. So that's all. So I'm done. So I finally would like to end up saying that Dr. Banerjee was one of the greatest inspirators, not just to me, but to many researchers of my generation. And I honestly state that I consider this to be a great honor in my career to be able to share some of the results with you and dedicate them in memory of Dr. Banerjee, a great teacher. And the principal theme is exactly what he also pursued all his life: structure, property, parameter, correlation. So why this material is strong, why this is magnetic or non-magnetic, why this is conducting or non-conducting, why this is transparent or non-transparent, the answer doesn't necessarily lie in composition. The answer more lies in the microstructure. So what is microstructure? How do you interpret? How do you understand? What are the tools? In some cases, optical microscope. In some other cases, very high-end, high-resolution microscope. Some other cases, some special spectroscope. So various tools we use for characterization and understanding. But essentially, we all try to form this correlation that for this composition or alloy, if I tailor the microstructure in this way, I get this set of properties. And in order to form these properties, these are the parameters that I should control and change. And then I get this. So that's the principle. So thank you very much for your attention.
Thank you very much, Professor Manna, for your inspirational lecture, which covers a personal interaction with Professor Banerjee. You have highlighted Professor Banerjee's excellent qualities and nice governance in making youngsters to be part of research and bringing this country towards a self-sustenance one. Really, it is an interesting lecture on microstructure. You have covered all the basics to advanced level, such including non-equilibrium plasma processing, discontinuous reactions, and you have taken almost all the basics of the metallurgy for, I think in your first beginning also you have mentioned it's going to be a second year engineering student. And you proved that you are a great teacher in bringing everything into a nutshell within a short duration. So certainly we understand that the microstructure is the reason, and once you understand this microstructure through various aspects, we can do wonders. And it is the new technology can be arrived through this kind of analysis of microstructure. Thank you very much for a nice and elaborated lecture on this program, along with the interaction you had with Professor Banerjee on this day. So I take this opportunity to thank you once again for a nice lecture. Now may I request our chairman, we ask Council of Management to give a small memento for Dr. Indrani Manna, a token of appreciation from our HBNI.
But Dr. Valtebra, I have a special request. You know, very rare to get such eminent people around. So why don't we also take a photograph? Yeah. I'll treasure that with you.
Can be opened or?
Yes, it is a little model of HBNI.
Okay. This is not glass, no? So why so much precaution is not going to break?
About in practice.
Oh,
Put it on your table.
very nice. Thank you.
Yes.
Thank you, sir.
I think somebody will take
Yeah,
that.
sure. Yeah, sir, I think all of us, Joshi is here, so. No, here it's.
Conclude and then take photograph. How?
We will just conclude the vote of thanks.
Oh, sure. Yeah, sorry, I didn't mean
That's
to.
audience.
Oh, I thought it's over now.
After that, maybe we can disconnect and, yeah.
Online.
Sure.
Good afternoon to all. So I am Professor Christopher Selvin, Registrar, HBNI. On behalf of all the family members of HBNI, I am so glad to be standing here to express my vote of thanks for this event to all the dignitaries assembled here and dignitaries who attended this great memorial event through online mode. So gratitude is a powerful catalyst for happiness. Gratitude makes sense of our past, brings peace for today, and creates a vision for tomorrow. I maintain that thanks are the highest form of thought and that gratitude is happiness doubled by wonder. So on behalf of HBNI family, I extend a really hearty vote of thanks to our chief guest, Professor Indrani Manna, for accepting our invitation and traveled all the way from Ranchi to HBNI among his regular academic schedule for delivering this memorial lecture with his inspirational thoughts of Professor Banerjee. Thank you, sir. I sincerely thank our most respected and beloved Professor Anil Kakotkar, Chancellor HBNI, for his presence and sharing the memories of Dr. Banerjee with us in this program. So I thank our beloved Chairman, C. K.N. Vyas, Chairman, Council of Management, and Secretary of Department of Atomic Energy for his presence and participation in this memorial honor offered to Professor Banerjee among his tight administrative assignments. So I thank Professor Ravi B. Grover, Institute Chair Professor HBNI, and Founder Vice Chancellor of HBNI for his presence and taking part in this event. So I thank Professor J.B. Joshi, Emeritus Professor HBNI, for his participation and paying tribute to the great scientist Dr. Banerjee. So I take immense pleasure in thanking Dr. N. Sai Baba, former Chief Executive of the Nuclear Fuel Complex, for sharing his reminiscence in this memorable event through online mode. So I take this opportunity to thank our beloved and Honorable Vice Chancellor, Professor Vasudeva Rao, the role model behind this great event that is taking place today here in HBNI. I take this chance to thank our beloved Dean, HBNI Professor P.D. Nayak, for introducing the chief guest today. I thank our own warriors, Dr. Maiti, Dr. Sureja, Associate Deans HBNI, for their excellent support in making this event a successful one. I thank Professor Tomer, Professor Paul, Professor Ghosh Professor Srikumar, Emeritus Professor of HBNI, for their presence here. So I thank all our respected directors, Dean Academics, and Dean Student Affairs of our constituent institutions for their participation in this memorial program through various online modes. I thank all the conveners of Board of Studies, deans, faculty members, administrative members, students from all our constituent institutions for paying homage and tribute to these great scientists. So I heartily hereby submit my heartfelt thanks to all the students of our HBNA family who has been benefited through this lecture by today's chief guest, Professor Indranil Manna. So I also submit my thanks to all the staff members of DAE families and other members of various other organizations for their participation in this memorial program. Not but least, I will be failing in my duty if I am not mentioning my administrative team from HBNI for making this event a highly successful one. I thank our Deputy Registrar, Mr. Danke, Mr. Bharati Swarna, Ms. Rita Rathod for their extended support. My special thanks goes to Shishyal for taking care of bringing the chief guest and safely and all the support making in this event a successful one. The team of academic and administrative teams have to be appreciated for their internal and external involvement in making this program a memorable one. The support of our office staffs, Mr. Sharma, Mr. Jaishwal, is highly appreciable. The audio and video support is the base for the function, and so I thank Mr. Anurag and Mr. Shab for making arrangements for this event. Finally, I may be apologized if I have forgotten to mention any names. Thank you all for your direct and indirect involvement in making this memorial event a highly successful one. Thank you all. Jai Hind.